So I'm going to start with a derivation. I'm going to do a derivation of basically a torque on a current carrying loop. And then I'm going to do a derivation basically of the potential energy of that loop as a result of being immersed in a magnetic field. And then I'm going to show you a couple applications that make that result kind of useful. So let's get started by showing you my dot cam. So what we want to do is we want to think about an actual loop of wire, but one that's sort of free to rotate so that I can think about torques and things of that sort. So I want to try to imagine a little spindle, if you will, that a wire could be attached to and another spindle on this side to hold the wire as well. But what I'm going to do is imagine a little wire coming from this side, going up, going across through that spindle, and then coming back down here like this. And I'm going to imagine the current going up on the right hand side. And then of course it goes over to the left. Then on the left hand side it goes down, comes back down here, and so on and so forth. Now I'm drawing it more or less in the plane, but I'm going to consider the case where the actual loop of wire, instead of being flat in the plane, I'm going to later consider it tilted at an angle so we can get a more general result. But right now I just want to draw it that way. What I'm going to do is say it's in a magnetic field, B, that's uniform, points this way, say. So that's our magnetic field. I'm going to say that this length right here is A, and that this length right here is L. Now, to think about torques, we got to talk about forces, and to get it forces, we got to remember our equation. Let's see if we can focus that a little better now. Seems to be focusing on everything but the writing. Still not very good focus-wise. Let's see. There we go. Okay, so I'll leave that focus in spot. Now, in order to talk about the force or the torque, we need to talk about the force. So we could think about using the equation dF equals I dL cross B. And assuming this magnetic field is fairly uniform, then this one length is just going to give us I times L times B, or F equals Bill, unless they're at an angle. So let's imagine from above what this looks like. So I'm going to look from above, looking down this way at this. And I'm also going to take that liberty of taking the plane and actually tilting it a little bit. In other words, taking the plane of the current carrying loop and tilting it a little bit, this side coming out and that side going in. So from above, first off, to get our bearings, we'll have the magnetic field still going from left to right, even when I look from above. So there's my magnetic field. But from above, I'll have the spindle in the middle. I'll have the wire over here. This is the wire, the top wire. And that top wire, of course, this side has the current coming out. So I'm going to draw that like a circle with a dot in the middle. And this side, of course, has the current going into the page. So I draw that as a circle with an X, or like we're looking at the back of an arrow. Okay. Of course, we also have current going this way, and I'll address that as well. So when we look over here, we say, okay, well, QV cross B are IDL cross B, because actually you could have also used F. Remember, current carrying wire, we imagine little positive charge carriers. So F is actually QV cross B. We just say, oh, well, these will be little positive charge carriers, so QV works as well. We'd have to turn it this way and then curl towards the magnetic field, and we see that the force in this case would actually go down. And then, of course, this force on the bottom edge would go this way, curl that way towards, on the bottom edge, going this way, would have to come out of the page. So this one's going to go QV is going this way. I got to turn this way. That goes into the page. And then on the bottom, it's going the opposite way. So QV is this way. And that automatically lets me curl towards it. So it's going to go up. So those two forces are going to go up and down. And they're not really going to cause any torque because they're going basically parallel to the rotation axis, which is this line right here. So we don't have to worry about the force on this one, which is actually a little easier to see it from this way, or this one, but because they're going to cancel each other out, and the net force that would exist would be parallel to the actual rotation axis. On the other hand, with this one, I've got a QV or a IDL coming out of the page like this, and I've got to turn it so that my palm can curl towards the B. My fingers on my right hand curl towards B. That means I'm going to get a force on this side that acts this way, and I'm going to call that F sub R for the force on the right hand side. Similarly, this one we have a current going down into the page. Using my right hand, my fingers are going to curl that way. I've got to be able to curl them towards the B field. That means this one's going to actually point this way, and I'm going to call that force F sub L. Okay. Now what you can see is, yes, these actually have a component of force that is both parallel to the lever arm, that's that one, and another component that is in fact perpendicular to the lever arm, that's that one. Same thing here, parallel to the lever arm, and again, perpendicular to the lever arm, and we'll call this angle theta. This angle theta. Okay. So with that in mind, we can see that the torque, which remember torque is equal to R, the lever arm, crossed with the force F. So what that normally does is just chooses the component. So if I talk about just the magnitude of torque, the component is just, or the magnitude of the torque is just the component of R perpendicular to F, or the component of F perpendicular to R. Either one of those will work. In this case, I'm actually considering the perpendicular component of F to R. And the way I get that is I write R times F times the sine of theta. So that's how I'd get the torque. And I already know the force from I dl cross B is just going to be F equals Bill. So I get a force to the right that's equal to B I L, and of course that points in, I guess, what I'd call the y-axis, so I'll call that a j-hat direction. And then the F to the left is again B-I-L, and of course that one points in the negative j-hat direction, so I'd say it like this, negative j-hat. And then when I want to know the actual torque would be R cross F. So I could just say R, which obviously points in that little perpendicular direction, but you're crossing it with J, and you see that you're actually going to get a tendency of this torque to rotate this loop of charge that way, or loop of current that way. Okay, so it's actually from above, it's making a counterclockwise rotation. So notice this one does the same thing. It tends to rotate it this way. This one tends to rotate it that way. So they're actually helping each other. They have the same sign. I don't have to worry about doing all the cross products. I can, but I don't have to. So I'm just going to say torque is equal to B I L sine theta. But I also need the lever arm. So the lever arm is actually going to be A over 2. That's one of them, plus the other one's going to add to it, B-I-L sine theta times A over 2. So I ultimately get that the magnitude is A over 2 plus A over 2. Of course, I factor those out, or if I factored B-I-L sine theta out of each, I'd get A over 2 plus A over 2 is just A. So I will now say B times I times A times L times the sine of theta is the total torque. Well, if you look at this rectangle, you'll see that L times A is actually the area of the loop. And it turns out that is actually the correct result, if no matter what the shape of the loop is. So ultimately what we learn is that the torque is actually equal to, in magnitude, BI area times the sine of theta, which you could actually define, for instance, a neat new vector. Let's take a new vector called mu. That's going to be what I will call the magnetic moment. And what we'll do is we'll define it to be basically pointing in the direction perpendicular to the plane. So it could be either out of the page, if this one was laying flat on the page, that is, which we sort of pretended like it's not here. But if it's laying flat on the page, it either points out of or into. So it's a little bit arbitrary. But if we force our right-hand rule, since we've been using so many right-hand rules anyways, to say that it has to be consistent with the right-hand rule, so your fingers curl in the direction current flows, then that dictates the direction. Then we have an unambiguous direction for this quantity. Now, what we'll find out is if we had two loops around here, I would have twice as much current, so I'd have twice as much torque. So what we're going to do, instead of calling the vector just I times A, we're going to say it's N times I times A. So it's N for the number of turns times I times a vector that I'm going to call A. And that A is that area vector. So its length is the equal to the magnitude of the area within the current carrying loop, and its direction is consistent with the right-hand rule. Now, if I do that, and then I can see, oh, wait a second, this I times A right here is just that mu vector, and this B is just the magnetic field vector, and then I got sine theta. That looks a lot like a cross product. So lo and behold, what I'm going to do is call the torque equal to mu cross B. So torque ultimately is just going to be equal to mu cross B, where mu is defined to be N times I times the A vector, and the A vector is defined in terms of the right-hand rule. So that's wonderful. That's given us a expression that looks just like torque. Remember, I said torque is equal to R cross F, and now I've found one just like it, except instead of R and F, I now have a mu and a B. So I got another cross product. That's handy. That helps us calculate some things. And not only that, it tells us that, notice as theta goes to 0, what's happening is the ring or the loop of charge is turning this way as theta goes to 0. And in fact, it wants the loop to be actually perpendicular to, or excuse me, the plane of the loop to be parallel to the magnetic field, which would mean the A vector is actually perpendicular to it. And when it does that, it has no torque. But if it's at any other angle other than this way or this way to the magnetic field, then it's going to have a torque on it. So that's kind of helpful. So now we'll look at the potential energy. The potential energy, U, is just equal to the integral of torque d theta. Again, talking about magnitudes here is not that big a deal, but when we put the magnitude in, we get N times I times A times B sine theta, which gives us negative N times I times A times the B cosine theta plus some arbitrary constant. Well, that's all well and good. What I recognize as NIA is, again, my mu vector, the magnetic moment, and B, of course, is the electric field vector. So a vector times a vector, or the magnitude of a vector times the magnitude of a vector times the cosine always tells me, oh, that's a dot product. So sure enough, what we're going to do is we're going to say the potential energy of a current carrying loop immersed in a magnetic field is actually equal to the negative of mu dot B, which I think you'll remember is not unlike the result we got for the dipole moment in an electric field. So now we've got yet another result. And remember, potential energy is the kind of thing that when it's a maximum, it's most likely to move the fastest to get out of it. And when it's down to the minimum, then it's really comfortable. And you can see that dot products, of course, always give you 0 when the angle between them is 90 degrees. So again, remember, mu is defined as a direction perpendicular to the plane of the ring, so it'll be like that. And then B, when that's perpendicular with B, you're going to actually get 0. So that's kind of interesting. Now, let me show you what kind of applications we could do with that. So for instance, one thing you might want to do is figure out a way to cause something to rotate. So if you actually took, say, a bunch of wire and wrapped it around something over and over and over and over and over and over and over again, and then put it between the North Pole and the South Pole of a magnet, then lo and behold, you're going to get this really strong magnetic field that tends to rotate this thing. Well, you can connect that thing to, say, transmission system for a bike or for a motorcycle, and then you have an electric motor. Or, more pressing for us in physics, if you take a little chunk of metal, say, and let's say it's iron, and we wrap a coil of wire around it, so it's going this way and then down and then under it and then come back up, wrap it around a bunch of times, and then have, of course, this free to rotate. So we'll have a little axle going through it and axle down at the bottom. Again, submerged in a north and south magnetic field. What's going to happen is these magnetic field lines, which come out more or less like this, but they're going to be drawn in this way and get even more intensely into the iron core. That's going to tend to rotate this thing. And if you actually set it against a spring, let's say we have a little lever that sticks out here and a spring that holds it, as the current that goes through here gets higher and higher, it'll have a stronger and stronger strength. We can just connect that to an actual pointer, and that pointer would in fact read something that's directly related to the current. That is in fact a galvanometer. So that is actually how a galvanometer works. You just have a coil of wire that's actually connected to the leads of the galvanometer. And as current goes through here, it tends to align this a specific direction based on how the spring was set and stuff like that. And of course, it wants to be at 0 when the currents are going this way parallel to the magnetic field. So that'd be the 0 mark. But as current went really fast one direction, or got really high one direction, it would tend to rotate it that way. And as it got really high another way, it would tend to rotate that way, again, depending on how you set the spring. So that's basically it. That's the sort of the last application, if you will, of the F equals IL cross B, or the F equals QV cross B, generating a torque on a current carrying loop. It introduces us to the magnetic moment, the mu vector. And you can see that has units of basically a pure number times current times amp. So it'd be amp meter squared. I hope that'll help you.